Go ahead.
Okay. Good morning, everyone. Thank you for coming to my talk. My name is Kira Lay. I'll be talking about wireless power today, or what I like to call how your electric toothbrush works. So hopefully you've all seen an electric toothbrush. You've got a plastic base that plugs into the wall, and then you've got your toothbrush. It's got a heavy handle on it. It's plastic. It's watertight. And if you look at the bottom, it's just plastic. There's no metal prongs there. If you look at the base, same thing, just plastic, no metal prongs. So we know this thing has power. We know it has a battery in it. So how the heck does it charge? So the answer is the electromagnetic property called inductance. And in this case, it's an application called inductive coupling. So inductive coupling takes advantage of a couple of physical laws that we should all know from our intro physics classes. The first is a current in a wire creates a magnetic field. So you may remember the right-hand rule. You put your thumb in the direction of the current and it curls around, yep. So that's one of them. The other is that a time-varying magnetic field induces a voltage in a nearby conductor. So this is a property of AC power, okay? So one thing about the magnetic field is it's inversely proportional to the distance cubed. So in order to make this work, we have to coil these wires, which increases the magnetic field and makes this property useful to us. So how does this apply to our electric toothbrush? Well, in the base, we have a coil of wires, call it an inductor, okay? And then in the handle, we have another coil of wires, okay? When we put that handle on the charger, then we have the coil of wires in the magnetic field that the first coil is producing, and then the current can flow into the battery because it's connected to that second coil of wires in the handle. So you'll start to see a lot of applications of this. One that you may already be using is your cell phone. We now have cell phones that have built-in inductors that can charge batteries, or you can buy a special case to charge your cell phone with, and you just have a pad that is connected to the wall, laying somewhere in your house, and you can just throw your phone on that pad and charge your phone that way. MIT is actually working on a way to power your whole room using a modified version of inductive coupling. And what you'll see is you'll have a hub somewhere in your room, and you'll have little inductive chargers plugged into all your devices. And they found a way through magnetic resonance to power all of your devices through this coil. So we may be living in a wireless world very, very soon. So that actually concludes my talk. Is there any questions? Yeah.
Can you expand on losses? I mean, I've heard people propose this for cars, but it seems really inefficient unless you have perfect resonance.
Yeah, so with regards to the MIT thing, I don't know a whole lot about that. It's with the resonance, I mean, the distance still really matters. They're only, right now, they've only got it perfect to about 1 meter. So it's still very lossy, but they're still working on that. Anything else? Yeah.
Are there any health concerns about having things all around your whole room go through your brain during the night?
Yeah, I mean, the power company gets complaints all the time that their new smart meters are making people sick, that sort of thing. As far as the electrical engineering and the professors that will actually talk to us about this sort of thing, it's inconclusive. They're still looking into it, but because of this property here, you would have to be standing very close to a very high-powered magnetic field for a very long time before you have to worry about anything.
Okay, so do you personally sleep with your cell phone on your knee?
I actually sleep with it under my pillow, yes. I'm not concerned.
Okay.
Okay. This took 5.5 minutes when I did it myself.
It's 3:39 this time.
Yeah.